Okay, YouTube, we've been exploring evaluating limits, and in this video we're going to visit a very profound property, and that's just the property of direct substitution with a lot of different well-behaved functions. So we've seen that sometimes, okay, the limit of our function of x as x gets really close to c is just whatever you get when you plug that x value into your function, because that would be the height that your graph is getting really close to. So we say that in those cases we can use what we call direct substitution, and direct substitution is just saying something like, if we take the limit of some function of x as x is getting really close to c, it just means that wherever we see an x, let's just go plug in a c and we can tell you what that y value would be. So by well-behaved, what do we mean? Well, we mean these are functions that tend not to have like discontinuities or holes in them. So we say that these well-behaved functions have this property of direct substitution, and this table that you see here kind of lists out 4 or 5 of these direct substitution instances in which we could do this. So the first one is this. We say letting b and c be real numbers and n is a positive integer. Then we could say that the limit of b as x gets really close to c is just b. In other words, if you take the limit of a constant, okay, then we get the constant there. And that's to say that if you were to go graph f of x equals b, this would be some horizontal line like this here that would always be at a height of b. And so no matter what x value you choose, say if we said x equals c right here, as x gets really close to this value, our function is always going to be getting really close to the same height anyways. So the limit of a constant is the constant. We also say that the limit of a line, or just limit of x as x gets really close to c, is you could just plug in the c value for wherever you see an x. You just get c. Same thing for a power function. We could say that a power function, any x to the n, if you take the limit of this as x approaches c, we could just go ahead and plug c in for x. We say it's c to the n. And last but not least, if you take the limit as x gets really close to c of some root function, some nth root, we can just replace the x here with the c as well for only even n here and c positive. So the last one we just say is just trig functions. Also, if we take the limit of a trig function of x here as x gets really close to c, we can just go ahead and directly substitute for that right there. So what we're going to do excuse me, is use this direct substitution property on these next set of examples. But before we do that, what I want to do is also explore this set of properties that we see here. So again, letting b and c be real numbers and n be a positive integer here. We let f and g be functions with the following limits. So basically, we could say that right off the bat, we are being told that the limit of our function of x here, f of x, as x gets close to c, is just equal to this number L. And the limit of our g of x as x gets really close to that very same x value is k, then we could say that these properties exist and we use them quite often. So we say that the limit of our function f of x times some real number b here as x gets really close to c is really equal to b times L. And so that is to say that we could really just take that b and we could just put it out in front. We could do the limit first of our function of x. So because b times L is b times the limit, then what you're seeing is we're just saying that we could do the limit first and then do the scalar next. Likewise, when we look at this next property, we say the limit as x gets really close to c of f of x plus or minus g of x is just L plus or minus k. That's the same thing as saying that, well, if you're going to do the limit of a sum, that's really the sum of our limits. That is to say that you could just do this here. And so, I'll hear people say sometimes like, well, that's kind of like distribution. I say, yeah, it's kind of like it. It's not really, but it's kind of like distribution here. So we say the limit of the sum of two functions is really the sum of the limits of those two functions individually. And likewise, the limit of a product of two functions is the product of those two limits. So we could do the limit of each function individually and then just multiply those together. And likewise with the quotient, the limit of a quotient is a quotient of limits, and the limit of a function to the power of something is really the limit of that function to that power. So to put these into play, just to show you why we want to have these properties and use them so quickly, is looking at something like this here on example 9. It says use the properties of limits that we had there to evaluate the following and use both tables and graphs to support your responses. So with what I want to do in this video is basically just kind of go through and say, well, because of all these being well behaved, let's use direct substitution. So we'd say the limit as x gets really close to 4 of x squared, what this would really be is just be 4 squared, because what we're doing is we're just plugging this into our function. So we really get 16. But to support this with a graph or a table, I suppose that if we went in here and we just typed in x squared, x to the power of 2, and I say, well, we were finding the limit of this as x gets really close to 4. So let me start my table at 4 here. We'll go by really small increments. But basically, as you look at this, we can see that our function very well is well defined there. I mean, it exists at 4. So instead of having to go through and make a table of this and say, well, what are our y values getting really close to, you can just directly substitute this in and say, there you go. So just like the same thing here, we'd say the limit of 5x as x gets really close to 4 would just be 5 times 4, 20, because at an x value of 4, our function would have a value of 20, and that would be getting close to that from both sides of x equals 4. So now looking at this trig function example, we say, well, direct substitution certainly applies here also as long as it's defined. And what we get is this right here. Now the tangent at pi, of course pi is this angle right over here, and on our unit circle we know that this is negative 1, 0, but to find the tangent, of course tangent's y over x, we really get 0 over negative 1 here. So 0 over negative 1 over pi, which is really 0 over pi. So in other words, we just get 0. And again, this would be really easy for us to support with a table or a graph. Now looking at letter D, the limit of this square root of x as x gets close to 9, we'll just say is the square root of 9, so really our function approaches a height of 3 there. The limit of x times the cosine of x as x gets close to pi here, we could say is really then pi in for our x times the cosine of pi. And the cosine of pi, we have cosine of pi is negative 1, we really get pi times negative 1. So our function would be really getting close to a y value of negative pi as our x value gets close to pi from either side. So our last function here, we have this x plus 4 squared. We want to know what is it getting close to as x gets close to 3. Well, hey, again, we're just going to go ahead and do our direct substitution with this well-behaved function. We get 7 squared. So our function would be getting really close to a value of 49 there. And it would be extremely easy to go ahead and support this with a table. Okay. So that being said, let's go ahead and wrap this up by looking at just a couple of additional properties. Basically everything that we just listed there. We said that we can use those properties above with direct substitution to evaluate limits of polynomials and rational functions. So remember that a polynomial, polynomial p of x here is just some function here, kind of like what we've got here, where we've got all positive whole number exponents and all real coefficients here. But this sum of terms then is some polynomial, and we could just use direct substitution on it as well. So the limit of our polynomial function of x as x gets really close to c is just plugging in c for all of our x values. That would be our limit. And also, if r is a rational function and we give r of x as some polynomial, and we say that c is some real number such that q of c doesn't equal 0, as long as this doesn't equal 0, then the limit of this rational function would be what you get when you just plug c into the top and the bottom. So looking at this here, we say the limit as x gets really close to negative 1 of this polynomial function would just equal what we get when we directly substitute this into our function. So we're going to go ahead and directly substitute this, and as long as we're defined, we should be good. We say negative 1 squared is 1, plus a negative 1 minus 6. This gives us really negative 6. So our limit here is negative 6. And likewise, over here we say, what's the limit of this? Well, we would say that it's the same thing as, and again, we would plug in a negative 1 squared plus a negative 1 plus 6 on top. That's our same function we did over here. But then on bottom here we get negative 1 plus 3. So our limit here, again, is negative 6 on top, but on bottom we get a 2. So our limit comes out to be a negative 3. In other words, if we were to go graph this function and look what happens to our y values on either side of x equals negative 1, from both sides our function would be getting really close to a value of negative 3. Cheers.